So, in the interest of getting us all caught up, since I had an absence, I'm recording these on my own. So, hopefully, that'll help you guys. All right. So, velocity vectors. So, now we're going to be using vectors in a way where it can model speed. In this unit, we will use vectors to represent velocity in models. So this is how you usually would use vectors. You would usually use this like in physics or engineering to just model two behaviors in a direction with an initial point and a terminal point. So make sure you watch this video on your own to kind of express more about how we add and subtract vectors. And as well as you can see vectors like this. It's a pretty cool video. Check it out. All right, so looking at this, if we're going to add vectors together, so if we have a force that's pushing it this way, and we also have another force pushing it this way, we're going to add these two vectors together to create what's known as R. So by adding these together, by adding this 2 and this 1 together, we're gonna end up getting a different vector. So it's a -2. I'm sorry. I was like, that doesn't seem right. Why is it -1? So because of that, we'll get a resulting vector, which is what happens when both forces are acting upon it. So instead of it moving this way and then moving up this way, we can see that both forces of the vector would just push it up this way. All right, so let's kind of try to solve one of these together. So we're going to be adding these two vectors, and then we want to find the magnitude of it. So remember, magnitude, this double absolute value looking thingy, what it is it means the distance. So in order to do distance, we basically just do the Pythagorean theorem. So let's get started on this one. Let me grab my tool here. And I've been out for a while, so I'm gonna see if I remember how to. Oh, apparently my tablet is not plugged in, guys. I am so sorry. Give me a second here while I get myself plugged in. Um, give me a second. I'm so sorry. Okay, so let's see here. There we go. All right. Unfortunately, it wasn't plugged in, so I wouldn't have been able to write on the screen. So when we're doing this, we're going to do the -2, comma 6, and we have the other one there. Well, you can see them right here. I don't think I need to write them out. So we need to add the x values together. We need to add the y values together. So -2 plus 4, comma 6 plus -9. So when you do this, you end up getting a +2 here, and we're going to end up getting a -3 here. And then we want to find the magnitude. So the magnitude is the Pythagorean theorem. Here's our x coordinate, here's our y coordinate, and we need to find this part right here. So we're going to do 2 squared plus -3 squared. And this will give us 4 plus 9, which will give us 13. So our answer should end up being like the square root of 13, which we can't really solve for because, yeah, it says approximately. So you're going to have to do this. You're going to have to do 13 and hit the little square root button. And that'll give you about 3.6. And this should be a 2 and a -3. I don't know why the -6 is not okay. Nearest, write the responses as decimals if needed. If that's to the hundredths. Okay, so I only did it to the tenths, 1 decimal place. So they want it to the hundredths, so it would be 3.61. So that one was just me not doing that. But that's all we're doing here for this one. Oops, let me erase the screen. All right, so now we're going to do a brief thing here. So in this activity, we're going to determine the relationship of the sum of these vectors. So find the magnitude of these two vectors together. So in order to find the magnitude, first we need to find the sum. So if we're typing this in, we would type it in as, let's have our vector here, and we would do -5 plus 3, comma, um, 2 plus -4. And that would result in a vector of 8, comma, -2. And here we would kind of have to use the equation editor. There's kind of no way around it. I mean, you can use the little symbols, but I think that's terrible. So we're going to do square root of 8 control up 2 plus, and if you guys don't like the control up, you can always use this little thing. I just use control up because it just lets me type into the calculator faster. -2 control up 2. This will give us the square root of 64 plus 4, and that's going to be the square root of 68. And it says round to the nearest hundredth, so you are going to have to type it into a calculator, and that would be, it would end up being 8.25 because the 6 will make it go up to a 5. Do that. Hit the submit. You can see all the work that they did. And wait a minute, what happened here? What did I do wrong? -5. Oh my gosh. So that -5, I didn't see that negative. Changes this to 2. So then we have, give me a second here. Highlight that, go here. So that changes this to 2, 4, 8, 8 square rooted is about 2.83. How'd they get 25? Wait a minute, what? -5. Are we subtracting these vectors? Give me a second here. Oh, of each vector. Okay. I got ahead of myself here. So give me a second. Either way, we have this down for both of them component form. So there's a component form. We just have it together. Calculate them. Calculate the magnitude of both of them together. Okay. So hold on. I jumped ahead, guys. I jumped ahead a lot. So this is how you calculate them together. This is going to be how you calculate the magnitude. So calculate the magnitude of the sum to the nearest hundredth. So that's here. One is to compare the vectors, you'll need to add up to find what is the sum in component form. So there's that. And this one, we were literally just supposed to find the magnitude. So we already know how to find the magnitude. Uh, Read directions, I guess, is the lesson here. So let's do the magnitude, which we said we had to do this way. So this is going to be the square root of -5 up plus 2 control up square root of 25. Now here's the part that's not making sense to me. They got 20. Okay, they didn't get 25. Okay, never mind. So parentheses -5 because it is part of your input. Like you are going to square the negative, so you do want to make sure it's in parentheses when you do have those negatives. Technically, we should be doing it for non-negatives too, but I especially show it when I'm doing the negatives. Again, it's 25 plus 4. Again, 29. So that's our answer. Well, not our answer yet because they want us to do the decimal. So do this, do that, and you get about 5.39 for this one. And then we want to do the next one. So we're going to want to do it for the U. So if you're lazy like I am, what you do is you just copy this, spacebar a couple times, Control V, and you're going to just edit this equation individually. So this we're going to change to a 3, and this we're going to change to a -4, which changes this to a 9, which changes this to 16. So we're going to end up getting 25, which reduces into a nice little 5. And that's how you get those. So calculate the sum of the magnitudes together. So that's just going to be the 5.39 plus 5. That'll give us 10.39. Submit that. 10.39. Then we have this. Submit it. And then we want the magnitude. Did I do this right? Hang on. Square root of 8. That doesn't make any sense. All right, we get that. How does it compare adding the magnitudes together? To the sum of the sum of the sum of the sum of the magnitude of the magnitudes, because there's two of them. The sum of the magnitudes of the vectors is greater than the magnitude of the sum vector. So what I'm saying here is like if I added these individually and if I found the magnitudes and then added them, it's going to be greater than if I combined them and then did it. And they did it as they actually wrote it out. So this is actually a little bit better how they wrote it. So they wrote the specific answers. So we're just saying that finding the magnitudes is going to be less than if we did them individually. Under these circumstances, part A is true. Under the circumstances, does the comparison hold true? What? Under what? Oh, okay. Give me a second. I kind of understood what it means. When is it that our vector sum will be this? So what it wants you to say is like, let's say we have a vector going this way and a vector going this way. Obviously, this ends up looking a lot longer or shorter than if we had the sums by themselves. So if we had a vector like this, Um, I'm trying to think of like that, the resulting vector should end up being bigger. So the reason why it ended up getting smaller is because of the fact that some of the vectors were in the same direction. So under what circumstances is true? Uh, when a component, so when we're talking about components, um, we're talking about the x or y component, x or y are in opposite directions. So well, the reason why this happens is because when we're square rooting, or I can actually type it in. The reason why this would happen is the absolute value will become smaller when adding. And I'll show you what I mean by that in a second. So um, let's see, where did I do the calculation? See here where, because we had a -5, that turned it into a -2. Actually, that should have been a -2, but I guess I didn't put the negative there. Um, so that's why I made it a lot smaller. But when we do this, these numbers are huge because it's a 5. It's not like a 2 or something. So this -5 becomes like a full-fledged 25. It's a big absolute value. This 3 becomes a full-fledged 9, even though combined together, it would just change it to like a small little 2, and or I'm sorry, a 4 instead of a 25 or a 9. So, and then let me read their explanations. So comparison to the true uh, do not have the same direction. So I said opposite direction. They're saying same direction. In comparison, if in the comparison you drew part E, is part E ever false? Under what conditions? When the components are in the same direction. Like I said, what I mean by that is, let me draw a picture. If we have a vector going this way and a vector going this way, it's gonna, like, the sum is gonna end up being smaller. But if we have a vector going this way and a vector also going this way, it's gonna end up going like way even further and create this really, really huge magnitude right here. Whereas this one kind of like dumbs it down. Just erase the whole board. All right, so the next one, same direction. So you can see here, these are in the exact same direction, and it gets a lot bigger. Could you come up with an inequality that holds true of any pair of sums? I would say uh, no, because of different directions. So part these are some relating equality for this. I guess it's saying it's always going to be smaller. Um, oh, because of no, because of different directions. So it would be yes. Just put an equal sign under us then. So because of the fact, the best you can do is have them be exactly the same. So it's always going to be like if you combine them together, it's always going to be smaller. So sorry about all the confusion, but that's how you do that part. So moving on to part 9. now we're going to be dealing with adding. Well, we already know how to add. So adding vectors is simply just like if this vector ends here, you're also going to do that vector over. You're literally just adding it. You're starting from you travel your u and then you put your initial point at the tip of u and go that way, and that's how you would add the vector. So this would be your resulting vector. All right, so now this wants us to so here's the magnitude, here's the other magnitude, then this is equal to um, a best case scenario if these are the same. Oh my gosh, I hate this. You can't really use the Edmentum calculator for this just because of how it works. So what I want you guys to do when you have to do vectors is go to desmos.com, graphing calculator, or not graphing calculator, I'm so sorry. Go to Desmos, Math Tools, Scientific Calculator. All right. So I don't know why they're having us do this because we proved that it doesn't work. Indicated at this angle. Oh, okay. What we're gonna have to do here. So what happens is we have a length here, a length here, and we have this. Let's say 4 square root 5, and we have another one here, which is um, 3 square root 5. We're going to actually have to use law of cosines on this. This one is 30 degrees. Okay, so we're going to have to use law of cosines here because we have these two vectors. That's obviously going to combine them. And is it going to combine? Well, we're going to assume that it combines them. We have to use law of cosines, which is kind of like the Pythagorean theorem, but we have this very long part right here that comes after it. So here what we're going to have to do is the C in this case represents this side right here. The, oh, I put 30. I'm supposed to put little c or big C. This is supposed to be big C, and I'll explain what that means in a bit. And it means the opposite angle of the side that we're calculating for. So let's take a look at this. So when we're doing this, we're going to square this part. So that would give me 9. So this is 45 plus um, let me plug everything in. 4 square root 5. And it doesn't matter what your A and what your B is, just as long as you kind of stay consistent with it. Square root 5. Oh, speaking of staying consistent. And then times cosine of 30. And cosine of 30 should give me a fraction. All right, so this would end up being 16 times 5. So what I did here is I kind of skipped the step. 3 times 3 is 9. Square root of 5 times square root of 5 is 5, so that's 45. So let me go back to Desmos here. I'm going to do parentheses 5, square root of 5. What I want the parentheses there, Desmos. 6 squared. So that's 80. So we're going to get 80 here. So 16 times 5 is apparently 80. Minus, oh, I'm just going to type all of that into Desmos. There is no way I'm going to do this. And actually, you can type this whole thing into Desmos. So I'm just going to go ahead and do that now that I think about it. Do this, square root 5 squared plus that minus 2. I'm lazy, so I'm gonna steal this, paste, paste, cosine of 30. Make sure it's set to degrees, which it looks like it is. So I get 21.07. Nothing even close to that. I don't know why it wouldn't be anything close to that. So let's see what they have for an answer. Okay, so they're literally just adding it. Oh, because they're in the same direction. Duh. They're in the same direction, it's equal. So ignore everything I just did. Sorry about that. Yeah, so because they're in the same direction, I didn't realize, I thought this would be that, but it makes sense that this doesn't work out because, let me show you why it doesn't work out. It would look like this. I was solving for this part right here. So that was my bad. You don't need log cosines. You just need to add these into Desmos because they're in the same direction. All right, so moving on to the next one. I'm actually going to leave it there. That was a hard one, and I need to contact other students. So you guys will at least have part one, and then I'll do the other 18 in a bit.